Okay, welcome. Oh, I guess we're just a little bit early. Okay, you're still welcome, but I'm not going to start now. Which one is this? Oh, I'm not. Yeah, I'll come out in just a minute. Okay, welcome. It is now, well, it depends on who you ask. The clock on the wall or the clock on the computer, it's either 6:01 or 6:02. So I think it's safe to get going. Tonight, we're going to talk about two sections in the notes, 2.3 on 2.2 on separable equations and 2.3 on exact differential equations. Let me just mention a couple of other things, though, before I jump into the lecture. The first one is this. Over the weekend, was it? I got caught up on grading, and so I made a summary report for everyone and emailed that out. So if you haven't yet checked your email, you should do that, because I'm sending out the reports for two reasons. First of all, just to inform you, it's nice to have that information. But secondly, there was one case when I sent out the report said that someone hadn't turned in a homework assignment, and they replied back and said, you know, I did send that to you by email. I looked at my email, sure enough, it was there. So mistakes can happen on either end. So a summary doesn't just give you information, it also is an opportunity to correct the record if there's something amiss. So please do let me know, and I'll be happy to look into it if you find an error there.
More
Thank you. Secondly, this just happened on the last homework assignment. It hadn't happened before. I got two different people who did their homework and scanned it. And then when they sent it to me, I couldn't print the document very well. And I finally realized what was happening. The scan was marked in some kind of way as if it were taking up a huge space physically. If I printed it out at full size, it would take many, many pages to print a single page there. And on my printer driver anyway, I have actually it's in Adobe Reader. There's a box you can click to shrink to fit, and it wasn't working very well. In one case, I couldn't get the document to print at all. And in the other case, with some few tries, I finally got it to where I think I can make it out. But if you could just double check and see, it may be that there's a single app, a phone app that's recently updated, and now you have to reconfigure it or something. So if you have any means for checking that, please do before you submit your next one. And if there's a problem, I won't jump all over you, but I will probably say, could you try again and see if you could get this to scan in a way that I can conveniently print it. But a certain amount of technical snafus are going to happen, and I guess we kind of have to make peace with that and fix them when they come up. But if it gets to the point where I really cannot print your document, then we got a problem, right? So eventually that bounces back to you. So let me see. Okay, last thing I want to mention, I got to switch cameras to do it, is at the beginning of the course, there was at least a book that I had started from when I started making my notes. And this is also the case in this part of the course, except, I could zoom out, but if I do, then it'll have everything wonky for the rest of the lecture. This book right here, Erwin Kraitzig's Advanced Engineering Mathematics, which I think is an excellent, excellent book, has a lot of the material that I have drawn on for the differential equations. This particular one that I have here in front of you, I have multiple copies of this in different editions, but the 8th edition is when I started using it for this course, and I love it. It's got such practical stuff in it. I have to. You can see right here, he actually intends this book. This thing it's like an encyclopedia volume. I don't know if you can see on the screen. It's very thick. And so I won't be bringing it to class much. It's a lot to carry around. But he intends for it to cover multiple courses, or courses that have multiple topics. And the thing I like about it is it has kind of a practical flavor to it. And he picked that up just in the title, right? And so I recommend that if you want a resource, and a really, I think it would be best for you if you had one, would be to look for one of these online. Now, if you get the 9th edition or the 6th edition or something like that, I don't think it makes a whole lot of difference. I do know that in some areas, there was some areas got a major rewrite on the 8th edition. So going much back before that might not be a great idea. But this 8th edition is pretty old. Let's see if it's in here. Seems like it should be. There's the publishing information. Well, somewhere, right there it is. Copyright 1999. So that's a ways back, right? That's like 22 years ago. So this book is still in print, and it's not in the 8th edition. It's way down. But if you're buying books, what you will find is that textbooks that are a few editions back from what's current tend to be pretty cheap. So that's another thing I really like about it, is if somebody wants it, you know, you can get it for a reasonable price. These crazy things now, I don't know. Last I was paying attention, books like this were oftentimes selling for, I don't know, around $150. And I don't know what it is like today. What are you seeing for, like?
It was a couple $100, like
Couple hundred?
300 maybe, I don't know. I got that one pretty cheap though.
You got a copy of this one? How much did this cost? Do you remember?
It was less than $20.
Oh, less than 20? That is a deal. You should buy it for $20. Especially if your intention is to be a practicing engineer or scientist. There's just stuff in here that is so helpful to just look it up. And I have to say, when I went through graduate school, in a certain kind of way, I was perceived, at least by many of my peers, as working in applied mathematics as opposed to theoretical. But when I got out of graduate school and I started teaching out of books like this, I learned a lot because I had a shipload of theory and not very much information on how to actually make it practical. And I don't know, you might still feel like my course has got an awful lot of theory in it, but trust me, compared to what it could be, the practical compared to the theory it leans heavily in the direction of what you could use as an engineer or a scientist. So I recommend that book. I think it's great. And the nice thing about it is you have these problem sets, and then if you look in the back, there are also answers. So there are things you can practice and you can check. And for these older editions, you know, frankly, it's not very hard to find things like study guides people have written and some solution manuals, stuff like that. It's really, really helpful. And so I recommend it to you. But of course, it's not required because I frankly can't require it. The department, it has this system for choosing textbooks, which is that they choose a textbook without reference to the person who's going to teach the course. And that's done by a committee, I think. And the expectation is that we'll just go along with it. But the particular book that was chosen for this, I actually don't think it's a bad book, but I do think it's not a great choice for the people who take this course. It's very theoretical. And I thought, my students want to be able to solve problems. They don't want to memorize theorems and write proofs. So the last signals I got were that it would be okay if I didn't follow their book. But it is a little bit awkward to require a book that isn't the one that's required in the bookstore. So that's why I do these notes. But occasionally you will find things in the notes, such as in the current set, which will have something that's clearly taken out of some other book. Well, guess what? Advanced Engineering Mathematics by Kraitzig would be a place to look to see if you get a match. And in this, for at least a couple of things this week, you will. I think there were cases when I was in graduate school, I was absolutely sure I had professors that were doing that. They were drawing from one or two sources, but they wanted to keep it a secret. They didn't want to say which one it was. I thought, why don't you just tell me? I can read that book too, but I don't know, they didn't. So, so I'm telling you, that's where I started from. Sometimes less so in this section than in linear algebra. Sometimes I add things that aren't in the original source that I think are helpful. For this basic differential equation, so this is so standardized. You pick up a book by any author on basic differential equations, they're pretty much going to go through the same stuff. There may be more or less theorems, but the content is a lot like calculus 1, 2, and 3. It's been pretty well standardized over time. Okay, we are going to begin by learning to solve some differential equations. And the first kinds that we're going to be looking at are called separable equations. Those are equations that you can get into this form. Some function of x times dx equals some function of y times dy. And the point of this is you can get the variables separated. One variable exclusively on one side of the equation, the other variable exclusively on the other side of the equation. Of course, these could be y and t, they could be a and b, any old letters you wanted. But the idea is you can split them up. And then if you can, then oftentimes, not always, but oftentimes you can solve the equation by taking antiderivatives. So this is the simplest method we have for solving differential equations that isn't just out of a Calculus 2 book. Now, or a Calculus 1. So for instance, this is a differential equation. Y prime equals 2x. What's y? Well, you would say x squared plus a constant, right? You're just taking an antiderivative. So that's the simplest level of differential equation. The next simplest is you have to take a step before you get it to that place where you can do the antiderivatives. So rather than wax eloquent or boring on the subject, what I'm going to do is just some examples, and I hope that this will be enough to get you started. You will find notes, and of course problems are posted on the on Blackboard. And I have tried in this, at least so far, to get at least brief solutions to at least some of the problems, because you know, you do a lot of calculation, it's really easy to make a mistake, and it's nice to have a check. So you will find some of that. Okay, here is our first non-trivial differential equation. And I lifted this out of Kratzik somewhere. So I didn't make it up, although I could have. This is not a very difficult one. All right, now what we are trying to do is to get our equation into this kind of form. X is on one side, Y is on the other, or whatever variables, just get them on opposite sides of the equation. And that's pretty easy to do in this case. Y prime equals minus 2x. And there's a step that really troubled me a lot when I first studied differential equations, which was that my professor did this next, which this did not bother me. And then the next thing he did was he, quote, multiplied through by dx to get this. And then he said, gosh, this would look better if we put an integral sign in front of it. And then he proceeded to take antiderivatives. And by the way, if you do that, it will solve the equation. Now, the thing that was bothering me is because in Calculus 1, he drilled into me, this is not dy divided by dx. This is not a fraction. It is a single symbol. It means the same thing as y prime or y dot or any of the other things you might use to represent a derivative. But then when it became convenient, he was willing to change his point of view and multiply through by dx. And I've heard various explanations, but let me tell you the one that I've heard that works the best. It's the one that physicists tell their students about quantum mechanics. You get into some stuff in quantum mechanics that just seem to make no sense. And the answer, I'm told anyway, I'm not a physicist, I'm told is that they say, shut up and calculate. And if you do it, you get the right answer. So I'll leave off the shut up part, but I'll say, look, if you just do this, you'll get the right answer, all right? So let's do it. Antiderivative of y with respect to y is y squared over 2. Antiderivative of minus 2x with respect to x is minus x squared. And then I think I will do this once so that you'll see why we don't need to. Normally, if you take the antiderivative of y, you'd get plus a constant, right? And if you took the antiderivative of something involving x, then you'd also get a constant over there. We don't bother writing on both sides because we could do this next. we could subtract that C1 from both sides of the equation. Whoops, not equals. Plus C2 minus C1. And then you reason like this. Well, suppose we took an arbitrary constant and we subtracted an arbitrary constant. What would we have? An arbitrary constant, right? So then, if you really wanted to dot all the I's and cross all the T's, and I assure you we will not in the future, as you could say, I know there's a certain disadvantage to having a left-handed lecturer, but I've not found a solution to that yet. Okay, what you could say is, well, we'll set C3 equal to C2 minus C1, and then this would be a perfect equality with what we had before. But normally we don't bother. We just put the constant on one side or the other, and we make it plus or minus as it's convenient and things like that. Because the next thing I'm going to do is multiply this thing through by 2. And I suppose I should, if I'm gonna write this with great care, shoot, I would write 2C3. But what happens when you double an arbitrary constant? Well, you get an arbitrary constant, right? So this would be y squared equals C4 minus 2x squared. And then I could take the square root of both sides. And of course, I can't tell whether it's going to be the plus or minus square root. So if you wanted an explicit form for the solution, it would look like this. And you know, there's some restrictions on this C4. You can see here, with this expression under here can't go negative. Otherwise, we couldn't take the square root. So this C4 is going to have to be itself, well, it's going to have to be non-negative. But if it were strictly 0, this isn't a very interesting solution. It's the function that's equal to 0 when x is equal to 0 and is defined nowhere else, right? So it's a function that consists of its graph is a single point in the plane. Not very interesting. So we will, to have any kind of a curve out of it, that C4 would have to be strictly positive. And the more positive it is, the longer the interval is that this is defined on. Now, this is fine. This is a good solution here. It is what we call an explicit solution. It's explicit in the sense that we have, if you give me an x, I can go through this process to tell you what the y is, right? It's just the formula is sitting right out there. It's a direct calculation, and the plus or minus, we should understand that this is representing two different functions, the positive square root and the negative square root. And if you want to know which one is in play, well, you'd have to have some information about the curve, like maybe an initial condition or something. However, sometimes the implicit solutions are actually a little more useful. So let's go back to this step right here. I'm just going to continue from there by adding 2x squared to both sides. And once again, you can see that this is only interesting when C3 is strictly positive, because if it were negative, you can't add up two squares and get something negative. There'd just be an empty set that this represents. And if you made it 0, well, then its graph is the single point, which is the point at the origin, 0, 0. So positive is the only interesting thing. And if we were to put this in standard form from high school, it would be something like this. Oh, let me think here. We want to divide through by, oh gosh, I don't like that at all. I'm not going to put it in quite the standard form from high school. I'm going to divide through by 2 is what I'm going to do. And I'll just call that C4, where C4, oh, I have already used up C4 earlier in this calculation. C5, where C5 is equal to C3 over 2. And we've already said that's positive. Okay, now, in this form, you probably recognize this as the equation of an ellipse. If you wanted the standard form, you divide through by the C5. But if you have x squared, ax squared plus by squared equals a constant, that is the equation for an ellipse. And if you wanted to take a particular one, you could take this one. What if C5 were equal to 1? So I'm not trying to list all solutions. I just want to get a look at one of them. That gives me x squared plus y squared over root 2 squared equals 1. And that, the graph of that is an ellipse. If you set y equal to 0, then x would be equal to plus or minus 1. So let's kind of sketch this out a little bit. So let's say that's 1 unit right there. So plus and minus 1 right there. And if you set x equal to 0, then the y would be plus or minus root 2, which is 1.4. So that'd be like up in here somewhere. So, and if I could draw, I would sketch in a beautiful ellipse that would make you all wonder, gosh, how does he do that? But as it is, I'm going to draw what I can, and you're going to think, so glad my notes look better than what's on the projector. Well, I'm glad to. So this is root 2 up here. Intercept here is minus root 2. So it's an ellipse that's taller than it is wide, and it is centered at the origin. And all of these curves, then anything parallel to that, you know, you'd have another one in here somewhere, and you'd have bigger ones out here. Anything parallel to that curve would represent a solution curve to this differential equation, which, you know, it's not bad. We started with a pretty simple equation, right? And, you know, it's not terribly complicated yet, but we did in fact get fairly rich set of solution curves. Okay, does anybody want to ask a question about that before I do another one?
Are the constants, like, are they all just arbitrary?
Yes, unless there's some restriction, such as in this case where it had to be positive. But we usually try to note that. Yeah. Generally speaking, the answer to your question is simply yes. Okay, well, let's move on. Here's another one. Example number 2 is y prime equals 1 plus 4y squared. And let's put an initial condition on this one, y at 0 is equal to 0. Okay, now, in this form, it almost looks like, whoa, we don't even have an x. Well, yeah, sure we do, because we have been writing derivatives as dy dx. And this one is not at all hard to separate. All you have to do is divide through by this, dy, divide by 1 plus 4y squared is equal to, and then we multiply through by the dx. And of course, if it helps any, it's 1 dx. And as long as you can remember the calculus formulas, you're good to go, right? So I'll just tell you the way I have it memorized. You may have memorized an equivalent form, but I'm not being so terribly clear on the difference between u and a here. So that is a u, and that is an a. So du over a squared plus u squared is equal to 1 over a arctangent u over a plus an arbitrary constant. So if it's been a while since you used that one and it seems unfamiliar, it comes up a lot in this class. So you'd want to remember it. Okay, now this one is not quite in that form, right? It'd be nice if we just had y squared here, and then we could have something else squared here. So what I'm going to do is divide the top and the bottom of this fraction by 4. So I've got 1/4 dy. And of course, I'm not going to leave that as a 1/4. I'll just multiply both sides of the equation by 4 to put the 4 over there. But I want the algebra to be such that you can follow the notes later. And then when I divide this thing through by 4, I get 1/4, which by the way is 1/2 squared. And what I'm trying to do is kind of match this pattern over here, du over a squared plus u squared. Well, if u is equal to y, then I've got u squared here, I've got du in the dy, 1/2 is equal to a, and this 1/4 is the only thing in the way. Of course, you could leave it here, just pull it outside the integral. On the other hand, I can multiply both sides of this equation by 4, like that. And now I've got a nice form for integrating. So the formula says I have 1 over a, so 1/2 is 2. Arctangent u over a, well, u is equal to y. Dividing by 1/2 is the same as multiplying by 2. And then when I take the antiderivative of 4 with respect to x, I get 4x and our ubiquitous constant. I forgot the 1 in the arctangent. And at this point, as far as we know, that C could be absolutely anything. We'll think about that in the future, but the arctangent, that has a graph that looks sort of kind of like that. It goes as high and as low as you want. So sure, it could be very, very positive, very, very negative. Anything in between wouldn't matter. So let's divide out this 2. Arctan 2y equals 2x. Now I could say plus c1 over 2, but I think I'll just call it c2. And if you want to be persnickety, then I would just add this and it would be fine. For the most part, I'm not persnickety about these. People who do a lot of differential equations, they just get to where they recognize, oh, it's just an arbitrary constant. They just change the name rather than make a complicated expression. Okay, so this is the solution to the differential equation, which we started with way up here. Y prime equals 1 plus 4y squared. However, it would be a lot nicer if we took the tangent of both sides. So 2y is equal to the tangent of 2x plus a constant. And then if we divide it through by 2, we would have an explicit solution. And at this point in time, we didn't, at least I didn't notice any need to restrict this constant at all. So I think we're good to let that be whatever it is. Okay, now that tells us that our solution is a tangent curve. Let's see. We have not yet applied our initial condition. Y at 0 is equal to 0. So if we're going to get that, by the way, a lot of people would mark this as a y sub g. I'm writing so tiny there, you probably can't see it. YG, it means general solution. That's what the G is. And then to find out of, this is a whole infinite family of curves, right? So to find the solution that has this property, you're looking for the particular solution and cleverly enough, that's usually labeled as y sub p. So what's yp? Okay, yp at 0 is equal to 1/2 tan 2x plus c2. Whoops, that's supposed to be a 0 there, which is equal to 0. Y0 is 0. So I've got 1/2 of the tangent of C2 equals 0, and I can multiply through by 2. Tangent of C2 is equal to 0, and now I realize I actually have a lot of choices, right? The tangent curve, actually, when I said arctangent before, I sketched the tangent, but anyway. So there's a sketch of one branch of the tangent, but you get infinitely many of those. So any of these places so that it intersects, so that you're at a y-intercept of the y equals tangent of x curve would do for C2. But how about this? C2 equals 0 would be a nice choice, right? But the period of tangent is pi. So this is at pi over 2, and the next intercept occurs here at pi. So there is a solution that will work, but in general, any multiple of pi would also work. So, you know, we didn't actually get down to a single solution here, but yp equals 1/2 tan 2x will do. That's what I'll say. I'll just leave it at that. And in an applied situation, you know, this curve probably is supposed to represent something. And generally speaking, you do want the simplest equation you can work with, but you might have a reason to choose one of these other options for the constant. It might make sense in the context. But for right here, that's about as good as we can do. Okay, so how do these things go along in general? Well, what I'm trying to illustrate with these examples is, first of all, it can be just quite straightforward. You push some things around, do some divisions, take some easy, straightforward antiderivatives, and you know, you work it around to your solutions, and you're done. Every once in a while, when you do that, you will come across a formula from calculus that may have gotten a little dusty. So just be aware, you need to watch for those. If it were me, I would probably start making a list of these as I work homework problems. You know, if I have to look something up, well, just write it down and then rememorize it. You probably did it once in calculus anyway. And then sometimes it just starts out with such an awful mess that it seems like there's really nothing you can do. To get the thing separated, and therefore you're at the limits of what this method can do. Now, I should point this out. The first part on the what I wanted to say was the hard drive, but it's not. It's a solid state drive. Now, in the solid state drive of my computer, I have 3 different folders for this class for lecture notes. The first one is basic linear algebra. The second one is basic ordinary differential equations. And the third is topics in differential equations. So in this section, basic differential equations, what you get are just multiple classes. Here, if an equation fits these features, then here's a method you can use to solve it. So we're going to walk through, I don't know, half a dozen or 10 different methods. If it fits like this, then you can solve it this way. And the one we're working on right now is if you can separate the variables, so get x's on one side, y's on the other, then you're good to go. You can solve the equation by separation as long as you can do the integrations. Now, when you look at this though, you think, okay, what could I do to get the y's on one side and the x's on the other? This does not look very hopeful, right? I've got y prime and y out here. I've got another y inside of a secant function of all things. Oh my word, this does not look like a friendly problem. So in the original text from which I drew this, they use it as an illustration of this substitution. And it comes with a comment. Every once in a while, there's a substitution that will just really make things a lot simpler. So we're actually going to do a couple of examples where substitution really helps, and hopefully things work out nice. Okay, now this is a common u equals y over x. If you're working with it in this form, this is the standard way of doing it. I did not invent any of this, and neither did Kraitzig. You just multiply through by x, and then you take the derivative of both sides. So that the derivative of y, of course, is y prime or dy dx, as we'll label it later. But then when you take the derivative here, you have to use the product rule. So u prime times x plus u, and the derivative of x is 1. So that's what y prime looks like. Now, the thing that would motivate it here would be that you see y over x inside of a trig function. So, you know, that's hard to deal with. Now, you might have thought, well, maybe we could put this term on the other side, divide through by x squared, and then take the inverse secant. That would get the y out of the inside of the trig function. That's true, but it would put it on the inside of another one. So it just, and what would you rather work with, secants or inverse secants? I think probably secants are better. So this one, if you're going to do it by separation, is probably going to be done with a substitution, a trick to simplify it ahead of time. And in this case, it really does kind of clean it up. So what we're going to do now is translate this. Every time I see a y, I want to write it in terms of u. So y prime is going to get replaced. X times y prime is x times u prime x plus u from this equation right here. Then that's equal to y, but y is equal to u times x. So it's a change of variables from y to u. And y over x, well, that's what we're calling u. So that really does help in there, and actually doesn't look too bad already. It appears better. Okay, now if we multiply this thing out, you'd have u prime x squared plus u times x equals u times x. That looks like a happy accident, but of course it isn't. That's the reason this particular ODE was chosen, because things get nice after the substitution. So you subtract u times x from both sides, and you're left with u prime x squared equals x squared secant of u. Well, that's not too bad, because we can divide out the x squared. And I'll just kind of do that by scratching it out, you know, that's gone. However, keep in mind that if I'm dividing by x squared, I have to assume that x is not equal to what? 0, yeah. So if x were 0, that would be a problem. So what that means is there may be a solution that comes from x equals 0, but I would have to investigate that separately. So I'll revisit that later. Okay, now in this case, this is pretty good. U prime is du dx equals the secant of u. Well, the reciprocal of secant, of course, is cosine. So that if I multiply both sides by cosine, I've got cosine of u du is equal to 1 dx. And then I am going to find the antiderivative of both sides. Okay, so the derivative of sine is cosine. So sine of u is equal to x plus an arbitrary constant, let's say C1. And I can take the inverse sine of both sides. U equals arc sine x plus C1. And then remember that u is not what we were trying to solve for. We were trying to solve for y. So that's y over x. Okay, so multiply through by x. I get that. And I have the assumption that x is not 0. And I have the initial condition that y at 1 equals pi, which I have not applied yet. So this is the general solution here. And notice they didn't put that initial condition at 0. And there was a reason for that. There's problems with this at 0. And actually, you can see it way back here, right? X can't be 0. So, okay, so if we set x equal to 1, gives us this, y is equal to 1 times the inverse sine of 1 plus C1, which is supposed to be equal to pi. How convenient. Oh, inverse sine. So how about if we take the sine of both sides of this equation here? 1 plus C1 equals the sine of pi, which is 0. So C1 must be -1, and that means the particular solution to this initial value problem is x arc sine x plus C1, but C1 is a -1, so x minus 1, and that's it. So this one gets a little more interesting. First of all, we had to do this substitution to get it into a form where we could separate it. Secondly, we applied our initial condition, and that got us down to a particular solution eventually. But you know, it's a little bit of calculation along the way.
I have a question.
Yeah.
So in the first problem, you were distinguishing between the constants. Is that something we need to do?
Generally, no. There are some cases where you have to be a little bit careful, but
Would we come across something like that?
yeah, I'm trying to think. Very often, even if you do have to, in general, if it did matter, it kind of washes out if you have an initial condition or boundary conditions or something like that, because then that forces the value of the constant anyway. So let me give you a couple of examples where at least somewhere along the way, it looks like there's some influence, but you know, in this case, it kind of goes away. So I think this is, what did I do last? Number 3. So this would be example number 4. Here I want to transition to some applied problems. So you start out with a physical description, and then you come up with a differential equation that models the physical situation, and then you solve. And oftentimes in physical situations, that is where you get some kind of boundary or initial value. And so we'll work on that. And it turns out we'll talk about constants a little bit more in this one. So how about this one? The rate of growth of bacteria in a culture, and keep in mind, the culture might be like in your body. It's the same principle. So the rate of growth of bacteria in a culture is proportional to the number of bacteria present. And we know a couple of things. At the initial time, at y equals 0, there are 20,000 bacteria in the culture. And we know that, let's say 4 hours later, there are 100,000. And the question is, how long before there are, well, I have this written as 25 million. Now, keep in mind, what we're going to do is, what this says is the rate of growth of bacteria in the culture is proportional to the number present. That's true, that sort of thing is true under certain conditions. So the bacteria are reasonably well spread out. There's ample room to support the ongoing growth of the colony, and also so that waste products that the colony produces are not interfering with their growth. If you are in that situation, and you are right at first, if you inoculate a culture, or like in your body, if you ate some food that was contaminated, then that's kind of what it would be like in your gut right at first. So that would say that the rate of change of the population, I'll let y be represent the number in the colony. The rate of change is proportional, so it's some constant times the number that are already in the colony. So that's it right there. This sentence gives us that differential equation. We're also given some boundary conditions. When we start measuring, we think there are about 20,000 bacteria in the culture, and 4 hours later, there are 100,000. And our question is, when will it hit 25 million? Now, of course, once the colony gets big enough that it starts being limited by the size of the medium that it's growing in, then this model is trash. That's not what happens at all. But for a while, you do get growth that is explained by this. Now, this turns out to be really pretty easy to separate. You divide each side by y, and you multiply each side by dt. And I got the t's on one side and the y's on the other. And what I'm going to do is simply take the antiderivative of both. And now I think back to my calculus formulas, and the antiderivative of 1 over u du is the natural log of the absolute value of u. So that's log absolute y equals kt plus some constant. Okay, so far, looks like that constant could be pretty much anything. And if you think about it, even if y is positive, if it's much less than 1, I mean, things that are close to 0 but positive, they have very, very negative logarithms, right? So this expression in principle could be very negative, could be very positive, could be equal to 0. If y turned out to be 1, the log of 1 is 0. So no restrictions at this point on either of those constants. Now, we'll take the exponential of both sides. So e to the log of something is just the something. So that gives me absolute y is equal to e to the kt plus c1. And now it starts to get to be a little heavy weather with the algebra. We got to remember that that could be written this way. E to the a times e to the b is e to the a plus b, right? You add exponents when you multiply like bases, in other words. And now this tells me absolute value of y is equal to, okay, now if I take e and raise it to a constant, well, I'll get a constant. However, there is some restriction here. If you take e to the anything, you definitely get a positive number, right? You don't get a negative. So C2 e to the kt, comma, where C2 is strictly positive. It can't be equal to 0 even. You cannot get a 0 out of this. But at this point, Jorge, you've probably already anticipated me. You say, yeah, but once you pull the absolute values off of this, then it doesn't have to be positive anymore. And I would agree with you, it doesn't. So let's call that C3. And now the only restriction is that C3 should not be 0, which is really kind of redundant. Because in this problem, I already knew this. The population is not 0, right? So it wouldn't have mattered. If I would have just blithely calculated along and said, it's a constant times e to the kt, it wouldn't have mattered because it would all come out at the end anyway. However, it's with a little experience that you learn when you can ignore this details and when you can't. Okay, now we're ready to start working. We know that at time 0, you have C3 e to the kt, or k0, and that has got to be equal to 20,000. So e to the 0 is 1, C3 is 20,000. So far, so good. So y at t is 20,000 e to the kt. And now we want to apply this condition that at 4 hours there are 100,000. So up to this point, we never really specified what that t is, what units it is. So I would probably just make it in hours. That would be convenient. So what I'm going to write here, t is equal to the number of hours since times 0. That means I can plug in a 4 here, as opposed to saying it's 240 minutes. E to the 4k is equal to 100,000. Okay, so we want to solve for k. 100,000 divided by 20 is the same as 10 divided by 2, which is 5. E to the 4k is 5. Taking natural log of both sides. So k equals 1/4 log 5. Or if you want to impress all of your friends who didn't pass high school algebra. It's the natural log of the fourth root of 5. How is that better than this? It isn't. It's just different. Okay, so now we have, now we know exactly which curve we're working with. Y of t is equal to, let's see, 100,000 divided by 20,000, that's, no, what am I doing? I already computed this. 20,000. E to the k, but k now we know is log 5 over 4 t. And I've scrunched that into a tiny little place so you can't possibly read it. But it says this, y is equal to 20,000 e to the log 5 over 4 times t. And we are trying to figure out, when is this equal to 25 million? So we'll do some calculation. All right, so we've got what? E to the log 5 over 4t equals 25 million divided by 20,000, which I'll write in a way that makes it easy to simplify. So let's see, we've got, this is 5 fours, right? And 10 to the 6 over 10 to the 3 is 10 to the 3. And, you know, there's lots of forms we could write this in. That'll work. So I've got log 5 over 4t equals 1.25 times 10 to the 3rd, multiplying through by 4 and dividing through by log t. And if I didn't botch up the algebra, which is a distinct possibility, this should come up with a correct answer. Did you do it already?
No.
Oh, okay. I heard buttons clicking, but I didn't know. Okay, well, here we go. 1.25 times 1,000 divide by log 5. Gee, I don't use calculators that often anymore. Log 5. And then I want to multiply by 4. Uh-oh. That's distinctly unlikely. Well, what did I do wrong? Did I type the wrong thing? Oh, I did, but I don't think that accounts for all of it. Let's just try this again. 1.25 times 4, 5 times 1,000, divided by log 5. Oh, silly me. Yes, yes, a minor detail here. In this form, when we want to get at that, we have to take the logarithm of both sides. So speaking of people who didn't pass high school algebra, I did. It's just been a really long time, and I guess I forgot. Okay, so take the logarithm of this side. And this is 1.25 times 1,000, 1,250. And then divide by log 5 and multiply by 4. And this should be more reasonable. You know, that number of hours, just that didn't sound right. So let's go after this again. Log 1250 divide by log 5 times 4. Oh, this I believe. 17.72 hours roughly. And this is under the assumption that the model is still a reasonable estimate for this long of time. Which, you know, 25 million bacteria for a lot of bugs, that's not a huge number, right? So you don't need a massive medium to support that. We've got, each of us, probably like billions of them in and on ourselves right now, so. Okay, so here's a applied example. And again, we solved by separation. And the thing that introduced this was Jorge's question about, you know, do you ever have to be careful about the constants? Well, in this case, kind of for a while it mattered, but you know, it washed out by the end. Okay, let me show you one last one, and then we'll leave. We will leave separable equations behind. But I want to do these two applied problems because they're similar to some things that show up in the homework, and it'd be nice if you'd at least seen some example. Okay, the physical situation is this. We have a 400-gallon tank. And inside of the tank is water and salt. And we are going to assume that we start with, let's say, 50 pounds of salt in 400 gallons in the tank. Now, the chemist among us will want to say, so do you mean 400 gallons of solution, or do you mean 400 gallons of water with an additional 50 pounds of salt in there? And I'm going to say, we're engineers and we're talking about mixing up some stuff and spreading it around on concrete or a dusty road or something. So we don't care that much. If it's off by a gallon or two, who cares? So we'll just blow over that entirely. So, and because I know most of you come for the entertainment of the artwork, I'll provide that for you right now. And I am aware that it's not because you're oohing and awing at how realistic this looks, but really it gives you something to laugh about afterwards and say, can you believe that picture he drew? Yeah. Keep in mind, I only draw the pictures that I can at least draw well enough that you could probably guess what I sort of had in mind. So these are not my bad ones. So this is the story this time. We're going to drain 5 gallons of mixture per minute out of this tank. At the same time, we're going to put 5 gallons of pure water in. And what's going to happen, and of course, you know, we need some kind of a stirring mechanism in here. And we're going to pretend completely against anything reasonable that the stirring is perfect so that the concentration of salt is always completely uniform 100% of the time, everywhere you look in the tank, which means somehow salt has to jump out of the tank and get into this water and distribute before it falls splash in the tank. Right? I don't know how all that works, but how do you do that? Computers and artificial intelligence can solve that problem for you. It can't, but trying to think of an excuse someone might give. Anyway, we're saying it's kind of close enough that our equations won't be completely silly. Okay, now, what we would like to come up with is a differential equation that would model the amount of salt in the tank, because we want to know this. When will the amount of salt in the tank be reduced to, oh, I don't know, 20 pounds? Okay, well, let's think about what this looks like. We need to say, we're going to let y of t equal the number of pounds of salt in the tank. And the rate at which the amount of salt in the tank is changing, well, it's going to be proportional to the amount of salt that's in the tank, right? You could actually figure this out exactly if you wanted to. I don't need to put a K here right now. I could say it's going to be the concentration of salt. And that's going to be what? It's going to be in pounds of salt per gallon of solution. That's what we're really working with here. Concentration, that's going to be in pounds per gallon, times the rate at which it's running out. Whoops. The rate at which it's running out is its concentration times the volume per unit time. 5 gallons per minute. And that will give us a rate, and the gallons cancel out, give us a rate in pounds per minute. That makes sense, right? Now, this concentration is simply the amount of salt in the tank divided by the 400 gallons that, move that. That's the volume of the tank. So the concentration is y of t over 500 times 5 gallons per minute. And I think we've got a differential equation. dy dt is equal to, now we could clean this up. I don't know if it's an advantage. It's y of t over 80, right? And our units over here would be pounds per minute. Okay, now, this, I rather suspect we can write it this way and simplify it. Let's just try this. You know, you can see the constants here, but I don't think it's not, I don't think it's going to matter at the end. So let's start with this, and I'll come back and sharpen it up if I need to later. Okay, so when I separate variables, I get dy over y equals k dt, and I integrate. So I get log of y, And I could be really careful and put in absolute values here, but you know, realistically, you're not gonna have a negative number of pounds of salt in the tank. So I'm not gonna get too excited about that. KT plus C1, so that Y equals C1, I said. Well, it's E to the KT plus C1. But then you split this just like we did before. It's E to the KT times E to the C1. So that is C2 E to the KT. So we get an exponential function again. And we do have some information here. We know at time 0, there is going to be, what did I say, 50 pounds? And that's equal to C2, because if you put a 0 in for T, this just turns into a 1. So that means my function is this, 50 E to the KT. And how do I figure out what the K is? The answer is I can't remember. I do know what. That's not very helpful. I know if you take the limit as t goes to infinity, you get 0, right? Which means that this k must be negative, but that we could have guessed that. The amount of salt is being reduced, so this function should be getting smaller rather than larger with time. So I do know this. Well, it turns out that it takes a very long time to solve this problem, mostly because my memory is failing me at the moment. So I will post this later. And then you'll see how I finish up the problem. Oh, I do know something. I know this, right? Think about at time, at t equals 0, I actually have some information. At the instant this starts, I know exactly the concentration of salt in the tank, right? I know that I have 50 pounds. This is easier than I thought. In 400 gallons of solution. Now that's going to be at that moment, you have the full concentration, 50 pounds in 400 gallons, and it's coming out at 5 gallons per minute. So y prime at 0 is equal to, oh my goodness, 250 over 400, which will certainly simplify, but the gallons cancel out. I'll get pounds per minute here, and that it's encouraging when the units come out right. Yeah. So we had an initial condition, but it has to do with the derivative, not the original function. Okay, so I think later has come. So here we are. We know that our solution looks like this: y equals 50 e to the kt. Oh, and I wrote, oh no, that's actually a correct statement. So y prime equals 50 k e to the kt. That's a chain rule factor. The derivative of kt is k. And then y prime at 0 is known. It's 0.655. And everything is going to be, weight is in pounds, time is in minutes, and volume is in gallons. So under those conditions, 0.655 is equal to, and if you plug in 0 for t here, you get 50K. So K, yes, I'm just thinking ahead about, I want my signs to come out right. So K is equal to 0.655. Oh, I see where it is. Okay, there's a missing minus sign in here, but it's easy to find. It's right here. So finally, I have an example where you need to pay attention. This K has to be negative. Why do I know that? Because the amount of salt is decreasing, so the derivative is negative. Okay, so way back here, how about if we wrote this as minus K, where K is positive? Then we could keep track of our signs all the way through. So you get a minus cascading all the way down to here. It'd be here as well. But once you plug in the 0, that one goes away. And we have minus 50K is equal to 0.655. And this minus 0.131. There's an extra 0 in there. Minus 0.0131. So y is equal to, what did we get? 50 e to the minus 0.0131 t. And now we can solve this other part of the problem. When will we be down to 20 pounds of salt? So minus 0.0131 t equals, well, what you do is, first of all, you divide each side by 50. 2/5 is 0.4. And then you take the logarithm of both sides. And then you divide through by this negative number here, which is good because this is negative, and dividing through by that negative, we get a positive time. And of course, as you have already figured out, there are some assumptions in this model that are not exact. You know, like the mixing is perfect and things like that. That's not true in any real system. So there's no sense carrying a bazillion digits here. It's just not going to be that accurate. However, log of 0.4 divide by negative 0.0131 gives me 69.9. And that was in hours, right? So it takes a while. to get rid of that much salt. On the other hand, if you think about this, 5 gallons per minute is coming out, and you've got 400 gallons of this brine solution in here. So it's a pretty small amount, a pretty small percentage of this mixture that comes out in a minute. So it takes a good long time to get rid of that much salt. Oh, did I have this in hours or minutes? Minutes. I had it in minutes. You're right. I like that better. A little over an hour. I guess I can believe that. 5 gallons per minute is, it's coming out. It's not dripping. It's like a garden hose speed. Okay, so that takes care of what I need to say about separable equations. And finally, I did come to an example. Too bad I didn't anticipate it ahead of time, but it really does matter what that the sign of that constant is here, right? So here would be a case. But Jorge, to get back to that question now, I think I can answer it with a little more directly. Once in a while, it does matter, and you do have to pay attention. But usually, there's something in the problem that will sort of trigger that thought anyway, so you recognize it. Okay, that is separable equations, and now we're going to do exact 2.3. Why don't we do this though? Let's take about a 5-minute break. At 7:30, I will restart. And what I'm going to do is just do some examples of exact differential equations. And you should be in pretty good shape to do the homework then.
So is there a homework due today? There is a homework due today, right?
Due in the sense that I'm hoping that you worked it, but not due in the sense that I'm picking it up.
So when does this one get picked up? The 2.1?
That is going to be factored into the next assignment that I'm going to post later tonight.
So
okay. So actually, I'm gonna come up with a fairly short assignment that I'm going to pick up on Thursday. But remind me when we're back in session. I'll say that.
So nothing's due Tuesday then as in homework? Well,
It probably will be.
Thursday.
Probably will be.
Thursday. Next
Yeah.
class, there's something due?
So Thursday there will be something due,
Okay.
but it will be relatively short. Because I mean, there's not much time between Tuesday and Thursday. But I've just found when you start a new topic, you don't want to wait too long because people get behind, overwhelmed. Okay, we're ready to get started. Tommaso, after class, I have some more paper here, so you can just pick it up.
Yeah.
In these early sections of the notes on differential equations, they aren't so much filled with, well, actually, it's oftentimes not a whole lot of theory and not even too many examples, but really kind of a summary of things you need to know in order to work on this. So what I'm hoping to do in lecture is to fill this out with examples, but I think you will find, having been through the lecture, if you scan what's in the handout, you will find some help in reminding yourself of how things go and solving some homework problems and stuff like that. So for instance, later on tonight, because we don't really have a lot of time, I'm going to use these formulas here, but I probably don't have time to derive them. But anyway, it probably doesn't disappoint you that much anyway, right? I've never felt like too many people were excited to watch me figure out the formula. So let me describe where exact differential equations come from and what we mean by exact differential equations. And then we'll actually create some and then solve them. But the way we're going to create them is we're going to pick a solution and we're going to create a differential equation that fits that. But the reason for doing that is to drive home what this thing means. And then we're just going to solve some. And then there is a method of solution, which we'll explain in just a few minutes here, called integrating factors. Because the standard thing sometimes doesn't work, but you can still rescue it. And you do it by the rescue operation is the integrating factors. And then all that'll get explained here in a moment. So let me pick an example here. I'm going to say a function u of x and y. And I'm going to pick something specific here. How about this 2x squared y minus 5 x squared y cubed. Now, there is a differential that you learn in multivariate calculus called the total differential of u. And its formula is simply this. It's the partial derivative of u with respect to x, dx, plus the partial differential of u with respect to y, dy. And that's it. That's the formula for the differential in u, or sometimes it's called the total differential. And the idea behind the word total is it takes into account both the x variable and the y variable. Now, this thing actually has a meaning. Way back in Calc 1, you learned this, that if dy dx is equal to f prime at x, then you, once again, multiply through by dx, and f prime at some starting point, x0, times dx is equal to the differential in y. And sort of the idea behind it is this. If you have a curve and you pick a point, so this is x0, y0, and you drew the line, I didn't quite do it there, did I? Line tangent to the curve, that if you were to move over a certain distance, call it dx, then the curve would change its height by a certain amount, change in y, delta y, but the line would change probably a different amount. In this case, it would be more. And this distance here is dy. And as long as dx is small, then following the line will get you to a place that's pretty close to following the curve. And, you know, I've sort of exaggerated it here. But in reality, if you have a curve and you just go a little tiny way along the straight line, the tangent line, you end up pretty much at the same point as if you followed the curve. Well, you can do that in 2 or more dimensions, but it's a little bit harder to draw. For me, it's just downright impossible. But imagine you have like a lumpy balloon. Okay, so it's kind of like a hill, and if you put a plane tangent to the hill somewhere, I don't know if I can even kind of make that work with the formula. If you put the plane tangent to the side of the hill somewhere, you could talk about moving over a little bit in the X direction and over a little bit in the Y direction. And if you followed the contour along the hill, you'd get to one place. If you follow the tangent plane, you'd get to another one. And that difference in heights that you get from following the tangent plane is what the DU is. Now, that's the geometry. Whether you understand it or not, I guess it doesn't matter, because we're not going to make any reference to it when we're solving differential equations. Other than this, if u were a constant function, then if you took the total differential of u, you would have to get the 0 function. By the way, when people, mathematicians write 3 lines in an equality, when they're trying to distinguish 2 things, in elementary algebra, sometimes you'd write something like this: f of x equals 0. And what that would mean is, suppose we knew now that that was x squared minus x minus 3 equals 0. So you're trying to find the x's that make this true, right? So that's one thing we mean when we write f of x equals 0. There's another thing that we mean when we write f of x equals 0. And if a mathematician writes it with 3 lines, they mean this: it is the 0 function. So in other words, it's always 0. It's not find the x that makes this true. Whoops, I'm off the screen here. It means no matter what x you plug in there, this is going to be true. So if ever I write the triple lines, I'm just trying to emphasize the fact it's the 0 function. We're not trying to find a place where that's true. So suppose u were just a constant. So your tangent plane, in other words, is just a flat plane. Well, if you move over a little bit in the x direction and over in the y direction, how much does the height change? Well, not at all, because you're on a flat plane, right? So the differential, the total differential is 0 if this u is a constant function. And that's really all you need to know about the geometry in order to come up with and to solve exact differential equations. Now, an exact ODE is one that is written in this form: some function of x and y times dx plus some other function of x and y times dy is equal to 0, where the partial of u with respect to x is that f function, and the partial of u with respect to y is that g function. And this is not the standard way of writing it, and so I will never refer to that again, but I'm just trying to communicate the idea that where one of these would come from is computing a total differential and then setting it equal to 0. So now you can see why I'm talking about creating and solving equations. Let's pick a u for this, for instance, this one right here. I'm going to create a exact differential equation from this. So the u, which in this case, and by the way, this is highly unusual. Normally you don't know the u, because if you did, you wouldn't need to do any work to solve the, or at least you wouldn't need to do very much work to solve the equation. So the exact ODE that comes from this u would be this one. You take the partial derivative of u with respect to x, multiply that by dx, take the partial derivative of u with respect to y, multiply that by dy, and set it equal to 0. Okay, so let's do that. Partial derivative of this function u with respect to x. Well, that means you basically, you think of the y's as being fixed, and you just take the derivative with respect to x. So I'll get 4x y minus 10 x y cubed. That is the partial of u with respect to x. And I'm going to need this one, so I might as well compute it. Partial of u with respect to y is, well, taking derivative with respect to y here, derivative of y to the 1 is just 1 dy. So this will be 2x squared. And partial derivative of this piece with respect to y is 3y squared times 5x squared. So minus 15x squared y squared. And now the ODE that we're thinking of is this one. You take the partial of u with respect to x, 4xy minus 10xy cubed dx, plus the partial of u with respect to y, 2x squared minus 15x squared y squared dy, and set it equal to 0. And by the way, doing something like setting a function like this equal to a constant is not completely absurd. If you think about smooth curves, this would, if you pick a constant here, you're just looking for the level curve. So I don't know if you've ever done any hiking with topographic maps, for instance, and you see these kind of funny shapes that they tend to be lines that sort of look like that. Well, these are the curves of constant elevation. So if these particular ones were going up a hill, it would tell you the top of the hill is right up in here somewhere, and it's got kind of a, I don't know, caved in side off of the hill or some such thing. So just because this is variable over here doesn't mean that this is completely impossible. It's just if there is a solution, it would be a curve along that surface somewhere, and all the points would be at some fixed height. Okay, so that is an exact differential equation. Now, why would you care if the differential equation you were looking at were exact? Well, the answer is that if you know ahead of time that you have an exact ODE, it's relatively easy to get the solution. We know that the solution in this case is u equals a constant. So you could say, for instance, equals k. Now, if I could reconstruct the u, and we'll talk about how to do that in just a moment, but if I could reconstruct the u, that would tell me that this is an implicit solution of that ODE. Why? Because if I took the total differential of this thing right here, on the left-hand side, I would get exactly this. When I take the differential of a constant, I get 0, and this would solve. So if you had something in this form, and furthermore, you knew it was exact, then you might be able to get the solution by somehow working backwards from the differential to the u. Now, let me take a simpler one, and then I'm going to solve it and show you how this would look in principle. Because, this one's kind of messy. So let's take one that's not so horrid. So u equals, this is deliberately simplified, 2x squared y cubed. And we will pretend that we're interested in a level curve on this. So this is equal to some k. I don't care which one. Maybe it would feel less abstract if I made this a number. Equals 5. Okay. So let's suppose that's my original u. Then if I take the total differential of this, well, I would surely get 0 because the differential of a constant is 0. And in order to use the formula for a total differential, du is equal to partial of u with respect to x dx plus partial of u with respect to y dy. And as we noted earlier, when you take the differential of a constant, you get 0. Okay, now the partial of this function with respect to x, well, that's going to be 4xy cubed. And the partial of this function with respect to y is 6 x squared y squared dy equals 0. And this is an example of an exact differential equation, ODE, ordinary differential equation. Now, this one is also separable, but nevertheless, if you want to solve it by exact methods, this is what you would do. Or there's actually two things you could do, but I'll show you this one. What I would do is I would look at this and I would say, well, what I know about this is it is the partial of some function with respect to x. So in other words, if I took this 4xy cubed and I integrated it, thinking of x as a variable and y as fixed, that should get me back to the u function. So let's just do that. So if we're taking an antiderivative with respect to x, then the y doesn't really count for much. It just goes along for the ride. It's constant with respect to x. So the antiderivative of x is x squared over 2. 4 over 2 is 2, so that gets me 2 x squared y cubed, and almost what I would like to say is plus c, but it's not quite plus c, because keep in mind there's a second variable around here. So this would be just any old function of y, but no x's. So it would look like that. And that, by the way, it does match the u that I came up with. Right? So in this case, that g of y is just the 0 function. It's not very interesting. Now, once I had made this discovery, once I had figured out that g of y is equal to 0, that would tell me that 2x squared y cubed equals a constant is the solution. Now, I'm not gonna belabor this one too much. I want to do another one so you can see why some of the details are coming in here as I do them. Last winter, I did a class that was completely online because, you know, we couldn't meet in person. And times like this were really hard to estimate. I had no idea how long it would take people to write things down. So I would just wait, too short, probably start again. If no one squealed, I kept going. Okay, so let's take a little more complicated one, but not too complicated. I'm going to take this one. Oh, sorry. And we're going to assume that we're interested in level curves equal to k. And now I'm going to write the ODE. The exact ODE would be this. It's just a formula. Partial u with respect to x dx plus partial u with respect to y dy equals 0. So if I were to create an exact ODE from this function, it would be this. 4x y cubed, then the partial of 2y with respect to x is just 0, right? Because no x in there. So that's constant with respect to x. So there's the partial with respect to x, dx. You don't really need the parentheses, but partial u with respect to y would be what? 6x squared y squared. And then the partial of 2y is 2 plus 2 dy equals 0. This is an exact differential equation. Its solution is u equals a constant. If only we could figure out the u, we'd be all done. Well, in this case, we know the u because we started with it, right? But now pretend that the problem started this way. It just started right here. This function times dx plus this function times dy equals 0. And the question that you would have to solve is this. Number one, is this an exact differential equation? That's the first question. Number two, if it is an exact differential equation, can I figure out what u is? And if the answer is yes, it's exact, and yes, I can figure out what u is, then the solution would be u equals a constant. So now let's recover the u from this, and I'm going to show you in more detail what that looks like. So what I'm going to do is take the antiderivative of this one, 4x y cubed with respect to x. Why? Because if this is exact, this is the partial derivative of u with respect to x. Okay, now, when I take the antiderivative with respect to x, I get 2x squared y cubed. But now, normally, you know, like Calc 1, Calc 2, when you take an antiderivative, you throw on a plus c, right? But what that means is something that's constant with respect to x. In this particular case, it's possible that that involved terms involving y, but not x. And in this case, it did, right? There's a 2y in there, and it's invisible once you get to here. So this is why you have to throw on that gy. Now, last time I didn't finish this all the way. So let's figure out, well, how could we figure out what this g thing is? What you could do is take the partial of u with respect to y, and now we know what the form of u is, it's this. So we take its derivative with respect to y, and we get 6x squared y squared, just differentiating the y cubed, plus g prime at y is equal to, now we have another expression for partial u with respect to y, it's right here. 6x squared y squared plus 2. And then you would say, well, these things obviously match up. And therefore, these terms must also match up. So that tells me g prime is equal to 2. And so g as a function of y must be 2y. Therefore, the original u must be equal to, well, we had it up to one term, right? We knew that it's 2x squared y cubed plus g of y, and we just figured out what the g of y is. It's 2y. Now, I should probably say this. Sooner or later, somebody is going to think of this, and they'll be right. They'll say, well, wait a minute. It could have had a constant on it, right? Because if you take the partial derivative of this with a constant, you still, whoops, if you take the, yes, you'd still end up with a 2. Because the partial of a constant with respect to y is 0. So that would go away. However, remember what the solution is going to be is a constant here. So if I had a plus c, then I could take that c and that k, put them together to make another arbitrary constant, and it wouldn't matter. So we don't normally worry about that because it all gets absorbed in this constant on the right. So this is the solution to the ODE. And it's an implicit solution. You know, it'd not be so easy to solve for y here. You could solve for x, but not very easily for y. So there's the solution. Do be careful. There's a tendency when people start with this method is they'll get back to the conclusion, oh, here, u is equal to 2x squared y cubed plus 2y, and they stop. So close, but not quite the solution of the ODE. Solution to the ODE is u equals a constant. Okay, so now let's try one where we don't have the solution sitting in front of us. And what I'm doing is shamelessly stealing from Kreatzig right now. So, but that's a good idea because we're running out of time and I don't want to pick a problem that doesn't have a solution or that has a solution, but it's awful. It takes 20 minutes to complete. Okay, so I have to answer really 3 questions. Number 1, is this exact? Number 2, if yes, find the function u. And then 3, set u equal to a constant to solve the ODE. That's the big picture here. So the first question I want to ask, is this even exact? It turns out that there's a pretty easy way to find out. If this is exact, this is the partial of u with respect to x, and this is the partial of u with respect to y. Now, if you are working with smooth surfaces so that it even makes sense to talk about level curves, then mixed second partials are equal. So if you take the partial of u with respect to x and then differentiate with respect to y, you get the same thing as if you start by differentiating with respect to y and then take the derivative with respect to x. So what you do is you find the second order mixed partial. Partial derivatives, I mean by that. So I'm going to take the partial with respect to y of 2xy. And I get 2x. And I'm going to take the partial with respect to x of x squared. And I get 2x. Those are equal. So yes, indeed, this is an exact equation. If these were not equal, it's not exact. So stop. You know, that doesn't mean there isn't some other way to solve it, but don't use this method. It does not apply. Okay, so now I have assurances that the equation is exact, and I would like to find the solution. So here's what I know. The partial of u with respect to x is equal to 2xy. Therefore, if I integrate 2xy with respect to x, it gets me back to u. Okay, so taking antiderivative with respect to x, that'd be x squared y plus anything that's constant relative to x. So some function of y. That's u. Now, let's go ahead and take the derivative of this u we just computed, partial u with respect to y, x squared y plus g of y. Well, that is x squared. Partial of y with respect to y is 1, plus g prime. And that must be equal to, go back to the original equation, that must be equal to this. This is assumed to be the partial of u with respect to y. So let me copy my equation here. Okay, so partial u with respect to y is that thing right there, x squared. All right, so subtracting x squared from both sides of that equation, we conclude that g prime at y equals 0, which means that g itself must be just a constant. And it doesn't matter, because what our solution to the ODE is u equals a constant. Usually call it k. So in this case, we figured out u. Where is it? U is right here. X squared y plus g of y, but g of y, we figured out that's just a constant as well. So equals k. So in this case, you can actually solve explicitly. Y equals k over x squared. The steps are these. Check to see if it's exact. Now we're starting with something like this. M of xy dx plus n of xy dy equals 0. So how do we know if it's exact? If partial of m with respect to y equals partial of n with respect to x, then it's exact. 2, recover u, and the way you get u is this. You could take the integral of m with respect to x. And that will give you something that you want plus any function of y alone. Then you take the then you match this up to the other term that's also the partial with respect to y. This and I said this wrong. You take the partial of this thing you just computed with respect to y, and that equals nxy. Solve for y, solve for g of y. And that gives you the function u of x and y. You knew it up to any piece that just had y's in it, or constants. So that's where you get it to there. And then u of xy equals k solves the original ODE. Okay, I will do more examples of this next lecture, but you've seen pretty much how it goes right now. What I haven't done, even talked about at this point, is this. Well, what if it's not exact? What then? Well, answer, maybe you can use another method, but sometimes you can make it exact. And you can make it exact by multiplying through by what's called an integrating factor. And don't worry about it, add it in the homework because we haven't even started it yet, but we will on Thursday. Okay, that's it. See you next time. And I do plan to post a hand-in assignment, a brief one, which will be due on Thursday. So please watch for that. It's going to appear in just a few minutes on Blackboard. Yep. And I got your other one right here. Yeah.
And that was the one that I emailed you.
Yeah, I couldn't never get it to print. So.
If there's any other format that I think I'm planning on handing in the other assignment, but if there is any other occasion in which I have to email it, is PDF okay, or should I?
Yeah,
change
PDF
it?
is fine. Since it never happened until the very last one of these homework assignments, and it happened to 2 people, it makes me think that one of these apps that people are using on their phone to scan them.
Okay.
Is that how you got your scan?
No, I've got a scanner. So
Really?
yeah, but I do know that it uses an app on my computer. So because it's not wired to the computer, it uses an app to connect it. And I think the way it imports the file is, I don't know, it could be different from a
Well,
wired
here-
connection.
Here's another possibility. Maybe Adobe Reader.
Yeah,
update.
that's what I'm thinking.
That
because
might have updated, so in fact, your scan is just fine, but my reader.
it could be, or it could be that the way it's imported in my computer is slightly different. It's not going to be compatible with, what you have in your cameras. But
We'll figure it out.
Yeah.
It's no big deal.